Why is it different from 3 sigma?
That's a good question, and that's a different kind of nomenclature because I think in this nomenclature you order it with increasing numbers of sigma bonds. But yeah, that's a convention that I don't like. Yeah.
And then all the one shell things are just bound around the nuclei of H and F respectively, right?
Yeah, exactly.
For fluorine.
Yeah. Yep. And so here, this matches really nicely because we have these 3 pairs of non-bonding lone, like in the Lewis structure, we would call them lone pairs, and here we're calling them non-bonding orbitals, 1, 2, 3, 4, 5, 6, right? All of these 2p electrons.
So which line here represents the actual sigma bond? Is that the 3 sigma?
Yeah, yeah, that is this bond, these electrons. Yep. Okay. So in this situation, this would be known as the highest occupied molecular orbital, and this one would be known as the lowest unoccupied molecular orbital. And it's just like it sounds. There's no trick to that. Yeah.
Isn't that just, I mean, the homo lumo, aren't they referring to the bonding, or is it just the entire structure?
No, any molecular orbital. Yeah. And so this difference governs a ton of things. And I mean, I'm sure there's a graduate course somewhere that's only dedicated to highest occupied and lowest unoccupied molecular orbitals. But suffice it to say that hopefully it's kind of intuitive that this governs a ton of stuff about the molecule, including its spectroscopy and its reactivity, right? And particularly in reactivity, whereas if a highest occupied and a lowest unoccupied have favorable energetics, then you can get a reaction. And we'll show an example of that here briefly. But in terms of spectroscopy, this is where these kinds of lines would fall. So here, if we're going from the highest occupied, the very highest of the highest occupied to the very lowest, which line do you think that would correspond to on here? The shortest one, right? The lowest amount of energy. So one of these values up here, right? Whereas down here, a higher amount of energy is going to maybe correspond either from here all the way up there, or from down here to there, somehow something that requires more energy, right? Okay. So you can also think about the lowest unoccupied as an electron donor, or excuse me, an electron acceptor, which is a Lewis acid. And this is characteristic of electrophilic compounds, right? So there can be different degrees of lowest unoccupied molecular orbitals. If it's a very, for example, if you would have a sigma LUMO, that would be very reactive, right? And so that can dictate the reactivity. The HOMO, the electrons are, they're electron donors, so that's your Lewis base. Okay, yeah.
What do you mean characteristic?
Say that again?
What does characteristic mean in this case?
Well, so what if I... So in this situation, if you're reacting ethylene with HCl, which one is what was your original question? What is characteristic of electrophilic?
Yeah, what does characteristic mean in this context?
So in this context, you would be thinking about what is your electrophile, right? So in this situation, this proton is your electrophile.
Oh, so it's the energy level of this orbital that determines it.
That's right, yes. So in this situation, this proton is electrophilic, right? It's seeking these extra electrons. So in this in this reaction, we're filling the lowest unoccupied molecular orbital of HCl via the highest occupied molecular orbital of ethylene. What's the highest? Do you know it without looking at it? What would be the highest occupied molecular orbital of ethylene? It's be a pi bond. Yeah, a pi bond. And that makes sense, right? Because we said that pi bonds are inherently less stable than sigma bonds, right? So therefore, they have more, they're more neutrophilic, right? Yeah, I'm sorry, nucleophilic, neutrophilic, of or relating to lymphocytes. So this is what that reaction, here it's written for fluorine, but it could just as easily be HCl, HX, right? Where this is a simplified version of ethylene if we were just looking at the two carbons where we have a sigma bond and a pi bond. And here we have the lowest occupied molecular orbit, unoccupied molecular orbital of fluorine is that sigma antibonding. So it's energetically favorable for both of these situations to drop down and form this new sp3 hybridized system, right? Yeah.
So we can say that the electron from the HOMO tends to fall to the LUMO, and that's what forms bonding.
Yeah. And you have these favorable, essentially overlaps, right? Because now you get to get rid of that pi bond and move it into this, a new sigma bond. Right? Now we've got 3 sigmas, no pi's, which is lower energy, right? Okay. Okay, so that's just, I just wanted to touch on those things. On to more nano-ish. So what if, rather than what if we had H3 or H4 or H212 or H infinity, right? What would that start to look like rather than just these two systems if you started to have many, a one, assuming you could make that. Yeah.
Is that what we call metallic hydrogen?
I don't think so. What's that? What the word we're going for here is an extended solid. Is the nomenclature that people tend to use. So got all of that. So in this situation, this one, right, is this is when the nodes are out of phase, right? In this situation is when they're in phase, and so we get something like that. Right? And for our purposes here, let's say that this energy difference between the bonding and anti-bonding is equal. That's an approximation, but let's say that this is beta and this is beta. Okay. So the overall difference between the two is 2 times that. Okay? And so if we call the original level of our ground state, which has a value of 13.6 electron volts. Yep. So then this situation is minus B. Okay? So if we had a third hydrogen, first of all, what do you think is going to happen to this distance. Because we've got another, we have to put in one more electron now.
It's going to be in the anti-bonding distance.
Well, so, go ahead. Yeah.
When you keep adding electron, like H's with electrons, it's
Yeah.
going to fluctuate between anti-bonding and bonding, right?
Yeah, kind of, yeah. Go ahead.
It'll add another orbital.
Why?
Because there's another this creates another space that the electron needs to fall into, and that ends up being a different. The electron's in that new physical domain created by the third hydrogen.
Okay.
It's at a different level.
Yeah.
Is it because it's you can't have more than 2 electrons without just
That's part of it, yeah, you can't have more than, but that's one of our fundamental rules of atomic orbitals too, is that we conserve the number of atomic orbitals and our number of molecular orbitals, right? And that, so anytime we were making these molecular orbital diagrams, the number of atomic orbitals always equaled our number of molecular orbitals, right? And that is a good point, right? Obviously we can't put in 3 electrons down here, right? Yeah. Not satisfying?
I feel like I should have a better explanation for why that happens.
Yeah.
When you have another proton, I can have an orbital around it, I guess. So it makes sense that it's not just going to lose its electron to them and then hang out over here with no electrons.
Yeah. Yeah.
But it would also change the initial energy levels. Because
How, right? Yeah. That was, I guess, the original question. Is this the distance between E naught and the new sigma bonding is going to decrease or increase? It's going to become bigger, right? It's going to move down.
But there's going to be a new orbital that's
in the middle. Yep. So we're going to get something that looks like, so let's try to draw it properly. So if this was our original, it could be slightly up here. Bonding. Okay? This one is going to become a non-bonding orbital. Okay? That's why I wanted to go back and talk about non-bonding orbitals. So 1, and then there's your third one.
What does this system actually look like?
This would look like,
These hydrogens connected in a row?
this is kind of a thought experiment. I'll show you. I knew someone was going to ask that, and I wanted to have a halfway decent explanation for it. So this is what people who model this computationally do. Is they pretend that it looks like this. Okay, where they draw these circles, squares, geometric shapes. Okay. Okay. So if we think about it in terms of phase, then these are all, not phase, but I guess the phase or the spin. The phase, these are all the same. This is going to have one this is why these are non-bonding, right? Excuse me, anti-bonding. And then this would look like, is that right? No. Okay, where these are essentially your 3 orbitals. These are not in phase. And there's no overlap in the middle, hence it's a non-bonding orbital. Okay? Yeah.
So the sigma on the bottom, what if that be like a oval?
You're saying, yeah, so if we drew this out even further, would it eventually merge like that? Yeah, because they're all in phase and therefore they can all hybridize. Yep. Yeah.
How is this different from the Venn diagram when we have like the conduction band?
That's exactly where we're going. Yeah, yeah.
Or is it not in relation to non-bonding?
Okay, so now it equals it. Yeah. These then are going to become the square root of 2 times beta. Well, wait, that's not right. This distance is the square root of 2 times beta. Okay. So what if we added yet another, what if we had H3? What do you think, what's going to happen to this distance? It's going to, again, increase, but how much relative to this? More than this or less than this? Less, right? And so when you push this out to H2, H3, H4, H, blah, 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 you start to see this convergence, okay? Where all of these lower energies are occupied and all of the antibondings are unoccupied, okay? And when you push this out very far, the delta E decreases with each additional hydrogen atom, and that's what we call a hydrogen or an extended solid, right? What's that? So then what this starts to look like is something like this. And so what people call this then is the density of states. Okay? Where the number of states are these bands, right? Or these energy levels. Okay? So if this was our hypothetical situation for H infinity, where you have more, at some level you have more and more states that are essentially become more and more equivalent, right? And that's why you have this asymptotic behavior. So that's what our imaginary situation looks like. And this is what it looks like in silica, right? Where you have you have this kind of, the valence, which is known as the valence band, which is your occupied orbitals, or bonding, if we want to call it like that, and our conduction band, which is our unoccupied, and which is our anti-bonding. Okay? So this would be the equivalent of our, where's the HOMO here? Right? If you can see, if these are shaded, hopefully you can appreciate that this is shaded and this is not, right? The highest occupied, I know it's always fun, that word, is right there, right? And the lowest unoccupied is right there. Yeah?
So what does the band gap in silicon arise from?
What does it arise from? The fundamental, the electron distribution of the electrons in silica. Yeah, go ahead.
So when more hydrogens are added, does it make more non-bonding sites or does it make more bonding sites? Or bonding antibodies?
So you get a new non-bonding per every other hydrogen.
But the energy level of it is
That will always stay the same.
and there's
Yeah, unless you would dope it. Yeah. So, well, yeah, this, you're saying, is there only one here?
Yeah, there's only one UMO, there's only one non-bonding orbital, right?
Yeah, yeah, yeah.
Can you explain like where the groups are coming from?
Why is it like this? Why is this not a completely smooth situation? It's probably because there are just certain energy levels that are much more favorable, and so it tends to fill those more quickly. But why does it look like that for
Does that refer to the different electrons that are filling up? Or like, where is that?
That means that at this energy level, there are a lot of states right here. Right? So at whatever energy this corresponds to, there are a lot of states, a lot of orbitals that have that energy. Right? Similarly, here there's not very many states that have this. And here there are none. Yeah.
Could this also refer to how it's phased out, like antibody and positive or something like that?
Yeah, I mean, you would when you have an extended solid, these have all theoretically approached the same level, right? That's why, like this kind of situation, I'm kind of fumbling on why there would not be a lot of states in that situation. But this is at least what it means, is how many, per energy, how likely are you to find a state and therefore an electron? Yeah.
It makes sense to me, I guess, that this is H infinity on the left side, so you've nicely added one proton, one electron the whole time. But in silicon, you have just an atom with a lot more protons.
No. This is not silica. This is like a million silica. This is not one silica. I'm sorry. Yeah, this is not one silicon atom. This is an extended solid of silica. This is a chunk of silica. Yeah.
So when you take those to infinity.
Yeah, exactly. Like imagine instead of taking H infinity, imagine silica infinity. Okay, we should put that in the correction. To do figure, whatever this is, figure SI infinity. Okay? So then this is known as, somebody said it earlier, but this is what's known as the band gap, that energy difference. Yes?
So we know pretty much how to do the molecular orbital diagram, but how do we go from that to the shapes of these things? So, for example, this is kind of like...
Yeah, you would never be asked to draw. This would be determined experimentally.
Oh, I see.
Yeah. So this is perhaps a better definition of what that x-axis is, the number of energy states per unit energy. So per electron volt, how many different states can I have, right? Per electron volt, how many different states can I have? The range of energies that an electron within a certain material can occupy. Okay, so do you have a lot of different energies or a very few amount of energies? Yes?
Could the groups also mean like the type of orbitals there are? Like, for example, a d orbital has like 5, or no, 3, sorry. Wait. I just
D has...
And D has 5, yeah. And then that would, like, and if we have an F orbital, then the spike would be more, just because there's more, like...
I don't think, I mean, by the time you get to these kind of extended solids, especially, those Ds and Fs have all blurred so extensively that I don't think that's the right way to think about it. Let me see what I can scrape up on this, but I think suffice it to say that this is, you're just thinking about the number of states that can exist at any given energy level.
States being like...
States being, this is one state that can have 2 electrons. Yeah.
So as you approach H infinity, it's pushing the band, and it's effectively pushing the band gap further apart. So
No. This moving this doesn't really affect Well, does it affect the band gap? Primarily not. I mean, band gap is a function of the type of material, the temperature. Yeah, I guess you can think about it that way. I mean, the way this is drawn here, there is no band gap, right? This is drawn as a conductor.
That's because hydrogen becomes a conductor when it's solid.
Okay.
Is it?
It turns it, well, if you
Is it? I don't
solid
know.
hydrogen, they call it metallic hydrogen. It behaves like a metal as it's cold.
It has like no unoccupied like conduction.
Yeah, and that's what happens to all metals, like when they turn into metal infinity.
Okay, I didn't know that. Okay, we did this. And so going back to what is a state, each state then is a solution to the Schrodinger equation. That makes sense, right? Yeah. Okay, so then what would this look like for a quantum dot? This is kind of the best one I could find is when you start to literally confine the space of these, the dimensions of these materials, you start to limit the number of states that you have, right? Because the electron can no longer move in these different dimensions. In a bulk situation, you can have an infinite number of states because the electron and hole, so let's come back to this. We need to build on this some more before we start to do these. Let's continue on with valence and conduction bands before we move to the nano part of it. Okay, so we valence and conduction bands. Valence we talked about, conduction we talked about. These are separated by what is known as this band gap right here, E sub G, okay? And that is characteristic of the material. So silica is about 1.17, cadmium telluride is 1.15, okay? So these lowest bands are going to be like your 1s orbitals, right? So boring, they're not going to do anything, they're always going to be occupied, right?
Do we still call them part of the valence band, or is that not even on this chart?
I think that they're valence. Yeah, even though they're core electrons. Yeah. Yeah, because these are now considered all of your electrons are essentially delocalized here. Yeah. Okay, so then if we were to draw this for a metal, we kind of talked about it already, right? But there would be essentially no break in between the valence band and the conduction band. Okay. And then what discriminates an insulator from a semiconductor is essentially how big is this band gap, okay? And so I think the rule of thumb is about 4 electron volts. Yeah?
I just noticed that this graph is now basically inverted of what it was before.
Yes. Yes, and so again, I mean, but look at like this. This is approaching this situation too, right? This is kind of inverted of what this is, right? And so I don't think you can, it may be that when you start to have these extended solids that the most probable energy state is not the lowest energy, right? That where the states are more likely to form are not necessarily at the lowest energy level. Okay. So metal, insulator, semiconductor, yes. Okay. Okay, so then defining a few more terms here. The Fermi level is in exactly 1/2 of the band gap. Okay, so the very, very lowest conducting energy state and the very highest valence state is the band gap, and the Fermi energy is exactly 1/2 of that. Okay? The Fermi level is the difference between the highest and lowest conduction band, and that can change with temperature. Okay? Yeah?
Doesn't the Fermi energy change?
It doesn't. It does not depend on temperature. It doesn't, because it's always in the middle, right? So if you have a situation like this, and then maybe you change the temperature and it looks like that, so you've dramatically tightened up the band gap, the Fermi energy is still exactly in the middle of it.
Oh, got it.
Right? So whether this goes up as the band gap increases or decreases, that Fermi energy is always exactly in the middle.
And this is a characteristic.
Characteristic of materials, yeah.
So, I'm sorry, I still have a question about the hydrogen. So, when you add another one, is it adding to the non-bonding orbitals? Or is it?
The way that I understand it is that it's a function of, is it even or odd? So if it was an odd number, that's when you had a non-bonding orbital. So like H3, H5, H7.
Okay.
But as you had an even number, you had paired electrons. And so there was no non-bonding orbital when you had even number of hydrogen.
They're happier in a bonding orbital.
That's right, which makes sense. Yeah.
And then when they're not filled completely, then they'd rather just do a.
That's when you'd have a non-bonding orbital, is H3, H5, H7.
So if it has a pair goes to it, it makes another bonding orbital?
Yeah. Yeah, so now here at H4, you have two antibondings, two bondings, two antibondings. Okay? And no non-bonding.
So is the reason that it doesn't have a band gap is because there are some electrons that occupy the non-bonding orbitals in the center?
What makes you think there's no band gap here? I mean, the difference between here and there, to me, would be the band gap.
Density of states, right? Like, why is there no break?
Why is there no break there?
Maybe this is just an approximation, it's not just an accurate.
Yeah, I to try to interpret like the real behavior of H4, I think is kind of difficult, other than doing it computationally. Yeah.
Does it maybe have to do with the simplicity of the nuclei? The fact that we, with hydrogen, we just have monocarbon nucleus versus silicon, something like that, we have a whole lot more.
Yeah, I wouldn't get too hung up on like how does H4 behave.
It would make sense more to me if the energy got closer and then there would be a lot more electrons that could go between the bonding and anti-bonding and it could conduct electricity better and it would act like a metal. In that, but when I look at this, I wouldn't think that it would act like a metal since the density of states.
Because these are becoming more and more different,
Yeah.
as opposed to becoming more and more the same.
Yeah.
Yeah, let me sit on that so we can push forward. Okay. So the Fermi energy is always 1/2 of the band gap. The Fermi level is this energy difference between the highest valence and the lowest conduction band at 0K. It's the energy state with a 50% chance of being occupied. So let's look at it, maybe graphically will help a little bit better. So the Fermi level at 0K is the highest level that's filled, okay? At 0K, it equals, again, 1/2 of the band gap. But so at 0 Kelvin, the Fermi energy equals the Fermi level. Okay. But the band gap changes as a function of temperature, and therefore the state that has a chance of being 50% occupied also changes with temperature. Okay? You can also think about it as the work required to add electrons to the system. or to put it into the conduction band, okay? And the way that this is calculated is through this equation, the Fermi-Dirac equation, where this expression is the probability that, and they write particle here. I would more think about it as state or band, right? Yeah, probability that a conduction band is occupied. Conduction band is occupied. Okay. E, so you want to think about this as like E sub I, because it's a function of the energy level that you're looking at, right? So if you're looking at an E sub I of really high, it probably all has a really low probability. So that's the energy level of interest. Okay. That is your Fermi level. And then Boltzmann constant and temperature. Okay. Let's work a problem and then we'll do the exam. What are the probabilities of electron promotion at 300 Kelvin into the conduction band? Let's just do silica. Silica at 1.17 electron volts.
I have a question that like counterintuitively makes sense that the probability increases as temperature increases.
You have more energy into the system and therefore it's more likely to move up into the conduction band.
Okay.
Right? So what we're given is the band gap. And what we need this, and we need this. In order to calculate this. Maybe I'll let you sit on that until next week, or until Wednesday. Okay, is this guy here?
Yes.
Oh, okay. So you haven't taken this yet, right?
No.
Okay, so,
That's why I have the office hours.
okay, so can you step out? Okay. Because I mean, I either have to make everybody wait until Wednesday to see their exams or make you step out. Okay, okay. Here were the scores. I thought they were pretty good. I mean, so 21, so there's like 70 people in the class and 44 of you got an A or a B. So it's hard for me to curve when 2 people got 101%, right? That really, I mean, generally when I've curved things, it's because the distribution is like skewed way down here. So like the highest was an 85, right? If the highest was an 85, it would be really tempting for me to curve this up. But, so Rosie, you got them? Are they alphabetized? So I'm inclined to let this, I'm gonna probably leave this stand. So if you have questions, you're welcome to come talk to me at my office hour